Good day. So, in this lecture we will discuss about SONET. The word SONET stands for Synchronous Optical Network, SONET, in the USA, Canada and Japan, or Synchronous Digital Hierarchy elsewhere. For example, in India we usually call it SDH. So, this is a time division multiplexing system that transmits a constant stream of information. SDH is actually a successor of PDH. Okay. Even a few years back we used to have a PDH gear in our telecom infrastructure in the wide area network part. So, that is plesiochronous multiplexing, nearly synchronous. Now, this business of becoming being nearly synchronous introduces a lot of problem and complication. Okay. So, when we from this nearly synchronous we went to synchronous, that was a major achievement as well as improvement of services, as we will see later on. So, in PDH multiplexing, in which two or more signals are transmitted at nominally the same digital rate and their significant instances occur at nominally the same time. Okay. So, this was PDH. Now, when SONET was introduced, it had a number of achievements to its credit. Firstly, it is a standard multiplexing using multiples of 51.84 Mbps, that is an STS-1 rate and STS-N. We will look at these rates. This was used as building blocks. This is something that is to be understood, that why is it that a particular rate value is so important. The point is, when you are multiplexing, the original source may come from various it may come from various sources, okay, and these signals will travel, will get together, will separate out and then mix with others, etc. So, that is possible only when we have an international multiplexing standard, alright, and this international multiplexing standard was first achieved in SONET. What happened was, previously of course the rate which people used were much less and being less, and they had all kinds of differences. Now, as technology grew and different sort of countries on different things came together, they came together at a certain rate of transmission, okay, and this is the basic building block of SONET. There is a standard multiplexing using multiples of this particular rate. So, that it in itself was a big achievement. Secondly, it also first stated the optical signal standard for interconnecting multiple vendor equipment. The point was, previously of course at lower rates they were all electrical signal standards. SONET has both a electrical signal standard as well as an optical signal standard, and in this optical signal standard it was possible to bring together multiple vendors to agree on to some particular format. And the third achievement in SONET was that extensive OAM and P capabilities. So, what are OAM and P? So, this is O is for operation, A is for administration and M is for maintenance, P is for protection. So, maintaining the system, administrating the system, operations of the system, etc., they are much more flexible in SONET compared to others. So, what kind of flexibility, etc., that we will see. Regarding protection also, SONET has a very strong point. As a matter of fact, it is so strong in SONET that we will sort of specifically discuss this aspect in a different, in a separate lecture when we talk about protection. So, these were very strong points in SONET, and that is not all. The fourth one was multiplexing formats for existing digital signals. You see, you always have, it is not that such a development can take place in vacuum. That means they had it had some history, and the trouble was that different countries had different kinds of histories, alright. So, it is not feasible for a technology to come and say, okay, throw away whatever you have been doing and then put this. Okay, that will never be. Such forklift upgrade is never possible because of cost, because of practical considerations, because of all kinds of things. So, an evolving technology, in order to be successful, most of the time it has to bring together previous technologies, and so that they can merge into this new technology, and that was another of SONET's achievement. These existing digital signals, you see this DS1, DS2, etc. These are different multiplexing standards at the low end. By the way, there is also a DS0, and DS0 rate is our venerable 64 kbps line rate. You remember once again that for voice channels we require 64 kbps because of PCM etc. that we discussed. So, that is a DS0 rate, and then several DS0 gets together to form DS1 and so on. So, that way there is a hierarchy of rates. Then the fifth achievement of SONET was that it supports ITU hierarchy, E1 etc. Alright. So, this ITU hierarchy was more popular in Europe, India etc. So, they had rates like E1, E2, E3 etc. So, E1 was something like almost like 2 Mbps, and then there was E2 8 Mbps, then E3 34 Mbps and so on. Whereas, the development in USA was in a different, on a different track. They had a T1 rate, then T1, T2, T3 etc. These were their rates. These are above this DS1, DS2 etc. So, what happened was that when SONET got introduced, these two sort of came together, and although they are not perfectly identical, this SONET and SDH, but for most of the part they are identical, they interoperate with only a very slight modification at the boundaries, which is not very important. So, that is a great thing. That is a great thing, that means that the same standard being adopted worldwide, so that any signal can be transported in any way. If there is an infrastructure, you can transport it in any way to another part of the world. So, there is no problem. So, this bringing together of that means bridging this ocean of Atlantic Ocean of these two standards, that was another good achievement of SONET. And next is that it accommodates other applications, okay, other applications which are not which were not a part of this kind of hierarchy, like BISDN, that is a broadband ISDN. So, that also can be accommodated in SONET. So, that way you see SONET was quite flexible. And how this flexibility is achieved, we will see that a little bit of that later on. And finally, it allows quick recovery from failure, as I was talking about protection etc. So, if there is a failure like a line failure, or if there is a terminal equipment failure, SONET can I mean if you deploy SONET in a particular fashion, then SONET can recover from this failure, and this retransmission etc. can take place within a very short period of time, and that is very important when you want to give carrier grade, so called the carrier grade service, where arbitrary downtime is absolutely not acceptable. Okay. As I said that we will discuss this separately in another lecture. So, some of the broad features of SONET and SDH, it was first standardized by ANSI CSA and now SDH by ITUT. So, a SONET was by this ANSI CSA and then SDH by ITUT. SONET is time division multiplexing pure. Okay. So, that means that we know what is time division multiplexing. So, how etc. frames etc. are made up, we will see that later on. So, it is a pure time division multiplexing system. And SONET encompasses optical and electrical specification. So, there are optical specification as well as electrical specification. You know that usually at the user end quite often things start at the electrical level and the rates are low, but as you go more towards the backbone of the network, the rates that are needed at the backbone starts becoming higher and higher, and finally at the real backbone there is it is a very high, it has to be a very high speed network, and such high speed network are only possible through optical communication and optical networking. Once again we will see about optical networking in the next couple of lectures. So we require so our specification, the SONET specification spans both the electrical side as well as the optical side, and that is a very good feature of SONET. SONET uses octet multiplexing. Octet, by the way, means the same thing as a byte, that means 8 bits. So SONET uses octet multiplexing, so they are multiplexed byte by byte, and SONET uses extremely precise timing, okay, something like 1 second in 30 years maybe. So SONET is, it is very precise timing it uses, and that is why things are synchronous, okay, and if things become synchronous then we have a lot of advantages we derive out of that. And SONET provides support for operation, maintenance and administration, OAM, as we have already mentioned. And SONET is actually superior to T3 and T4 etc., with improved, say, over the T carriers. This T3, T4, I mean they are still in use, but they feed into SONET nowadays, but earlier they used to feed into this PDH, and this T3, T4 are particular rates which existed, and their specification left something to be desired because of this lack of synchronicity. Handling them handling these signals from different sources, mind you. So what could happen is that when their things are not, I mean nearly say, I mean not synchronous but just almost synchronous, then this to handle this almost part you have to do something, you have to incur some overhead and you have to incur some complexity. Okay. So that is a that was the difficulty with PDH. Now in SDH, of course, so SDH or SONET, this is eliminated. So we get better transport performance. Okay. And then we have the ability to identify substreams. This was another advantage of SONET over PDH, which is that in a you know that a particular user may be using a very small kind of bandwidth, small in a relative sense, okay. And then as more and more users, as I said, that as all these data streams or communication streams come towards the backbone of the network, the streams I mean the pipes tend to get fatter. That means we need faster and faster communication. Okay. So between say 2 points in the backbone, there may be a very fast communication going on, and then after going to some other hops, then this will again diverge. Okay. Sorry. Now SONET has this ability that different streams can get together, travel for some time and then again diverge. Alright. So the ability to identify substreams, okay, that is very important, and that is also allowed in SONET, which was more difficult in the earlier systems. Then of course international connectivity, as I said that it bridged the Atlantic, so and that was great, and it enhanced control and administrative functions. That was also very good from the point of view of service providers. Now we have talked about this 7-layer OSI protocol. Where does SONET or SDH really fit in? Actually SONET or SDH goes to the bottom of this. That means if you remember that from starting from the application layer, we have right down right up to the physical layer. There are 7 layers in OSI model. There are other models anyway, but usually the bottommost layer is always the physical layer. So SONET really fits into the physical layer in some sense. Okay. So what would happen is that the layer just above the physical layer is the data link layer maybe, or layer 2. So after all these encapsulation etc. is over through these all these 6 other layers including this data link layer, only after that SONET takes it over for transporting it from one point to another. So SDH is placed at the bottom of protocol stack in the physical layer along with the fiber. Any IP traffic, even if it is an IP traffic which is a packet oriented traffic, and remember that SONET is a TDM system, but then IP traffic can sort of travel within a sort of TDM transport as they I mean quite often do. So, any IP traffic that is destined to be transmitted across a fiber based SDH network will be framed by a layer 2 protocol before being ready to take its orders from the SDH equipment. Now, these are some of the multiplexing standards. I have not given all of them, I just indicate some of them. If you remember that, as I mentioned, the DS0 is the that 64 kbps channel, and 24 of them constitute a T1 line. So, T1 rate is approximately about 1.5 megabits per second, 4 T1 gives a T2, 6 T2 gives a T3 and so on. Similarly, 30 DS0, this is another system really, that means this is the European system which gives an E1 line. So, E1 if you remember is about say 2 Mbps, 4 E1 gives a E2, E3 is a 34 Mbps line, okay. And then I suddenly jump right up to this thing called OC3, okay. This O is for optical. So, it is so this rate is 155 Mbps, which is 3 of the basic STS-1 rates that I mentioned earlier. I will come to this. So, these are some of the standards. So, there is a whole hierarchy of standard as for example, this name SDH also is a synchronous digital hierarchy. So, this is the hierarchy. So, the for SONET the basic rate is STS-1, that is synchronous transport signal level 1. The speed is 51.84 megabits per second. This is designed to carry what was DS3 earlier, or a combination of DS1, DS1C, DS2 etc. As I said that a combination of different streams can flow through a SONET SONET pipe. So, or a SONET infrastructure. So, that is good, that means say DS3 is a fat pipe or DS3 is almost the same as STS1. So, it is a fat pipe through which multiple say maybe DS2 or DS1 etc. they may travel. And this rate goes up to STS-N, whereas a synchronous transport signal level N. So, this has a speed of N into 51.84 megabits per second. So, designed to carry multiple STS-1. So, and these as I mentioned that these are byte multiplexed STS-1, that means one byte from one source, another byte from another source and so on. Fundamental SDH frame is STM1. Okay. SDH is the, if you remember, is the other standard which was there, which came from Europe, and then they sort of came together, that is what we are talking about. So, SDH frame is STM1, synchronous transport module, and SONET version is OC3, that is the optical container, each providing 155 megabits per second. So, when we come to this rate, this 155 megabits per second OC3, that I mean different rates etc. and different system they sort of culminated here. So, this 155 megabits per second, almost 155. STM4 provides 4 times the STM1 capacity, STM16 provides a further 4-fold increase. So, which means that STM4 may be about 620 megabits per second, and then if you go to STM16 which is 4 times that, that is about 2.5 gigabits per second. Then you have STM64 which is about 10 gigabits per second. So, all these rates are there. That means, from this point onwards these two streams have converged, and we are going to higher and higher rates also in a sort of universal fashion, which makes things easy across the world. It is worth noting that the internetworking between SDH and SONET systems is possible at matched bit rates. For example, that is STM4 and OC12 for example. So, so they interoperate. A slight modification to the overhead is required as they are structured a little differently. So, there will always be a little something, but anyway that is not very serious. So, they do interoperate. So, looking at, so we have seen at the SONET electrical hierarchy, now looking at the SONET optical signal hierarchy. OC1 is the optical carrier level 1, carries an STS1, OC3 carries STS3 or STM1, at 155 Mbps, OCN optical carrier level n. And so, OCN, as I mentioned, is an optical carrier which uses n into 51.84 megabits per second. So, OC48 is about 2.4 gigabits per second, or say overhead percentage is about 3.45%. OC signal is sent after scrambling to avoid long string of zeros and ones to enable clock recovery. Okay. This is a small technical point. That means that in order to keep the whole thing synchronized, the SDH units, they use the transitions which happen when there is a 1. Okay. So, the point is that if there is not a 1 for a very long period in the data stream, then the clock of the clock on one side may drift relative to the clock on the other side. So, that is always possible. So, we try to avoid the long strings of zeros in this SONET or SDH, and we do that by scrambling the data from various streams, etc., descrambling them. So, the idea is that even if one of them is sending a long stream of zeros, there will be quite a few ones from the other streams, and then the clock will be maintained by. Okay. And STS-N is synchronous transport signal, electronic equivalent of optical carriers. OC3, OC12, OC24 and OC48 rates are common in telecom circuits. So, if you remember, OC48 is 16 times OC3, that is 16 times 155 Mbps, so which is about 10 Gbps. So, up to 10 Gbps is very common these days. Actually, right now with DWDM system, OC 192 rate is already in operation, and OC 768, which is 40 gigabits per second, is being talked about. So, you see, so that was another disadvantage earlier, that this digital hierarchy, this hierarchy of standard rates, they did not exist beyond a very small rate. I mean, small of course in today's comparison, but now we have an extended and open system where we can always, as technology improves, we can always go for higher and higher rates. So, from OC3, which is 155 Mbps, we can go to maybe OC 192, which is 10 Gbps, or OC 768, which is 40 Gbps, which we are sort of being talking about now. Now, how do we use these high speed links? These high speed links of course have to be on fiber. So, we will look at details of fiber later on, but please note, in a practical application, an SDH line system will have a multiplexer that takes its input from a variety of sources in different layer 2 data formats. So, here we are talking about these different signals coming in the electronic domain, and they are coming from a variety of sources, maybe coming with different layer 2 data formats. These are aggregated up to form frames at a line rate of the system, for example, up to STM64 for a 10 gigabits per second bit rate system. Okay. Now, these frames at 10 gigabits per second, of course, you cannot sort of pump them anywhere it is very difficult to pump it on a copper. So, these frames are then transmitted out onto optical fiber links. There is the possibility of multiple SDH multiplexers to each give out one wavelength of a WDM system. As we will see later on, this WDM stands for wavelength division multiplexing, which is some form of frequency division multiplexing, as I mentioned about it when I talked about the frequency division multiplexing. So, in fiber optics we talk about wavelength division multiplexing. So, it is possible that one multiplexer is feeding into one wavelength, another multiplexer feeding into another wavelength, and all these different wavelengths are travelling together in the fiber. At the end of the system will be an SDH demultiplexer. On the other end, just as you have multiplexed on one side, naturally you have to have a demultiplexer on the other side, that now accesses the individual data streams from the STM64 frames as required. So, STM64 is carrying a lot of lots of frames in a very short time. So, they are sort of separated out and then fed into slower streams down the line. So, there may also be an SDH add drop multiplexer with the ability to remove and insert lower bitrate streams from the signal. Alternatively, a digital cross connect may be present with the ability to switch individual VC4s, well, which is virtual container 4, which is another concept, we will talk about it later. So, between different fiber links, that means there is a digital cross connect, you need not go into the, if you have a digital cross connect at the optical level, the advantage is that you need not go into the electronic domain at all. So, the advantage of not going into the electronic domain, one of the advantages is that you are handling a very fat pipe, that means a large number of channels, and you can just switch them from one fiber to another simply in the optical domain without doing any kind of processing, okay, and that is always an advantage. So, we will talk about some SONET terms now, for example, envelope. So, this envelope is the payload. Payload means basically whatever is being transmitted, meaning that after all encapsulation etc., you remember that finally at the near the bottom we have this layer 2, and this layer 2 protocol will encapsulate it and then hand it over to SONET at the lower level, maybe at the physical level. So, whatever this layer 2 hands over to SONET, that is the payload. Okay. The rest of it are the kind of system overhead. So, payload plus some end system overhead also goes into the payload. So, these two together form what is known as the envelope. So, this is just a SONET term. And other bits and bytes which are used for management, and that means OAM and P portion. So, that goes as the overhead of SONET. Then there is this concept of concatenation, that means unchannelized. So, envelope can carry super rate data payloads, for example, ATM etc. So, method of concatenation different from that of T carrier hierarchy, we need not bother about it at the moment. Then there are some non-standard or functional names in SONET, like TM is for terminal multiplexer, also known as line terminating equipment or LTE. So, these ends point to point links. ADM for add drop multiplexer, we have mentioned this. DCC for digital cross connect, wideband and broadband, we have mentioned this also. MNR for matched nodes, and D plus R means drop and repeat, etc. Anyway, these are just some terms. Okay. Now, let us come to some important concept in SONET, namely section, line and path. Now, what is a section? The portion from, I think I will just show you a figure first and then maybe come back to this. Please look at this figure. So, we have what we have is that maybe we have some multiplexers. So, as the figure shows, so we have a multiplexer on this side, another, so which is output feeds to another multiplexer. This multiplexer, so this is going in this direction, then after some time the signal becomes weak. So, we want a repeater, that means what is a repeater? A repeater is something which boosts the signal strength. So, there is a repeater, then it travels some more distance, and then there is a repeater again, and then it travels some more distance, and then on the other side now we have the corresponding demultiplexer, and then it feeds into the other demultiplexer. Now, from repeater to repeater we call it a section. So, or from a repeater to a multiplexer, this is also a section. So, multiplexer to repeater, repeater to repeater, these are called sections, and then from multiplexer to multiplexer we call it a line. Now, at the repeater nothing happens excepting the signal is cleaned up, okay. Signal may be boosted or there may be other cleaning operation, synchronizing operation etc., that may be done at the repeater, but as such the signals which are travelling here, the same set of signals are travelling here, okay. At a multiplexer, of course, some of the signals may go off in another direction, some signals may go in some other direction, etc. So, at the multiplexer there may be convergence or divergence depending on which way the signal is flowing. So, that may happen at a multiplexer. So, from multiplexer to multiplexer we call it a line, and then from the end user point to the end user point we call it a path, okay. So, sorry. So, let us just look at this once now. The portion from a multiplexer to a repeater is known as a section, or it could be a repeater to repeater also. The portion from a multiplexer to another multiplexer is a line. The portion from source to destination multiplexer, that means is a path. Below path, line and section is of course the photonic sublayer, that means photonic sublayer means whatever is happening in the optical domain. So, we are not discussing that at the moment. So, sections are bounded by repeaters or multiplexers that terminate the line and lines may carry several tributary signals. Lines are bounded by multiplexers. A path goes end to end between terminating multiplexers. So, we have seen this. Now, each STS frame lasts 125 microseconds. Okay. As I mentioned that this 125 microsecond time period, time epoch is sort of sacred in this whole domain, because 125 microsecond is what is required for a DS0 channel. Alright. Remember, this is a time division multiplexing, which means that if you have a 125 microsecond kind of slot, okay, then a DS0 some of the DS0 bits or bytes can take this route. Some of these bytes actually, if you take it, you have to take it 8 kilobyte per second, and if it is 8 kilobyte per second, inverse of that is 125 microsecond. So, if you have a 125 microsecond slot, 1 byte of, if it travels in this frame, then that is enough for one DS0 channel. Okay. Of course, we have a very now in SONET we have very sophisticated and very fast equipment. That means, fast means what? This is a time division multiplexing system. That means within this 125 microsecond, not only one byte can go, but a lot of other bytes can go. Okay. That means a lot of channels can travel together in this 125 microsecond frame. Okay. So, this is the idea. So, each STS frame lasts 125 microseconds. Now, how many bytes are going in there depending on whether it is STS-1 or STS-2 or STS-N, etc. So, 125 microsecond, as I mentioned, is 8000 frames per second. STS-1 frame has 6480 bits or 810 octets or 810 bytes. That means, in one 125 microsecond slot or frame, we are putting in 810 bytes. Okay. So, theoretically, of course, that means it can carry 810 DS0 or voice signals. Actually, it is not so, not 810, it is less than that, because a number of these bytes are used for this overhead, different types of overhead. So, we will talk about this. So, anyways, we have these 810 bytes. Okay. The octets are understood in terms of table of 9 rows and 90 columns. So, let us look at this figure. We have, so this is a SONET frame or an SDH frame, which have 9 rows. So, you can see there is 9 rows on this side and then 90 columns, okay, total 90 columns. Out of these 90 columns, 3 columns have been shown in yellow. So, these are sort of used for overhead, and these 87 columns are used for, most of them are used for payload or is used for the envelope. If you remember, the envelope contains the payload as well as a little bit of overhead, which we will come to that later on. So, this is how, so after every 90 bytes, we come back to again another 3 bytes of this overhead. So, this is how it is to be understood. The first 3 columns contain transport overhead, and TOH has 9 rows by 3 columns, that means 27 bytes, which is subdivided into section overhead, SOH section overhead 9 bytes, 3 rows of 3 columns, LOH, that is line overhead, which is 18 bytes, that is 6 rows of 3 columns. So, this we have a section overhead and we have a line overhead. Remember, we have these 3 concepts like section, line and path. We have not talked about path overhead. There is some path overhead also, and it goes into the envelope. So, there is some path in this thing. So, far as the line and section are concerned, these are the overhead bytes. just to clarify this, why do we require the overhead bytes? The point is that the multiplexers or the repeaters, they have to have some communication between them in the control plane, so as to for giving you this OAM capability, alright. So, for that some information needs to be sent on or exchange between the 2 points anywhere where there is a section. So, a section overhead would consider those things which are central to the section about the signal strength and other kinds of things. Line overhead maybe would contain something else, and similarly path overhead would contain something else, but these are required for these OAM capabilities that we have in SONET. So, let us look at these overheads separately. First, section overhead, which defines and identifies frames and monitors section errors and communication between section terminating equipment. So, these are its functions. It identifies frames, monitors section errors. So, section is a section overhead. So, in that section if there are errors, so it monitors section errors and communication between section terminating equipment. So, maybe 2 repeaters or a repeater and a multiplexer and so on. Line overhead locates first octet of SPE and monitors line errors and communication between terminating equipment. So, we will come back to this locating of the first octet of SPE. This is a very interesting feature and we will talk about it separately. Other standard line errors. So, previously we were talking about section errors. So, line errors and communication between terminating equipment etc., that is taken care of by the line overhead. Apart from that, line overhead contains this pointer really, which points to the first byte of the SPE. And then there is a path overhead, and as I said that path overhead really is inside the envelope. We will look at all this later. So, path overhead verifies connection. Path you remember, path means from end to end, that means from the end to end multiplexer, that is a path. So, whether the connection has been established or not, it monitors path errors, receiver status, communication between path terminating equipment and so on. So, this is the POH. Now, we talked about the synchronous payload envelope or SPE that I was talking about, that is the other 87 columns. This holds the SPEs, synchronous payload envelope. So, SPE has 9 rows by 87 columns which are divided into path overhead and payload, which means that the path overhead goes along with the envelope that is in the SPE, whereas other overheads have separate bytes or separate columns associated with them as shown. So, now the SPE does not necessarily start in column 4, okay, which means that the SPE does not necessarily stay within one frame. These are two very important points in SONET. The point is that although you have these 87 columns, but actually the data may get may start getting transmitted at some arbitrary point inside that 87 columns. Okay. Now, what is the idea? I mean, why do you want to leave something and then only start from the middle? The point is that if there are some kind of mismatches of because of mismatches of rate etc., if everything in the world were absolutely synchronous, all activities and all equipments etc., then you could have started from the beginning, okay. But that is not the case, and this is where we absorb this kind of variation, and this gives a great flexibility to SONET which was not there earlier. And the other thing is that, other interesting thing is that SPE does not necessarily stay within one frame, which means that the SPE may start in one frame and then end in another. We will just look at a diagram of this. Okay, let us have a diagram of this. You see the SPE, this light green color, that really starts from somewhere, I mean somewhere after leaving some of the rows, okay, it starts here, alright, and the path overhead is somewhere here, okay, and there are 2 frames here. So, SPE is really spanning both the frames. Okay. So, SP is not frame aligned, overlaps multiple frames. So, avoids buffer management complexity and artificial delays. Okay. So, so whenever you have there is something to send, you can just send it in that envelope, just put that pointer to that LOH. So, that LOH will point to the first byte of the SPE. It allows direct access to byte synchronous lower level signals, for example, DS1 with just one frame recovery procedure. So, these are the advantages, as I said, that the SONET frame. So, this is one frame coming in maybe 125 microsecond, this is the next frame, and my SPE, as I have already shown, can overlap. I mean, it may start from anywhere, I mean somewhere within the first frame and then continue in the second frame in this fashion and then be over, alright. So, you can so actually, and after this some other envelope may come in over here. Okay. Now, of course, then where does the path overhead really where is the path overhead? There are two fields H1 and H2 fields in LOH, which is there in line overhead. LOH means line overhead, so which points to the beginning of path overhead. Path overhead beginning floats within the frame, 9 bytes, that is one column, and it may span frame along with the SPE, originated and terminated by all path devices. Okay, and this gives you end to end support. So, these are the features of path overhead. The point is, if you remember that path is end to end, that means the end users, it is close to the end users. So, just as the end user may start somewhere arbitrarily in between. So, that is why the path overhead also goes along with the SPE and it starts over there, and at LOH we keep a pointer to this path overhead. Just some of the equipment that we use in SONET, and one of the most important of this is the add drop multiplexers. Add drop multiplexers, they are important because at a certain point in the network, what might happen is that there are some sources which want to send into the network. So, they will sort of go. So, there is this SONET equipment, this ADM, let us say, and the SONET stream is flowing, let us say, like this. Now, there may be something who wants to upload and travel along with this thing. At the same time, this may be the destination location for some of the other signals which originated elsewhere. So, they have to be dropped here. So, some signals have to be dropped, some signals have to be added. So, this multiplexer can handle that, and that is very important. So, that is why they are called add drop multiplexers. The stream itself is of course flowing at that tremendous rate, whatever that rate is. So, SONET SDH is a synchronous system with a master clock accuracy of 1 in 10 to the power 9, which you see is very highly accurate. So, its source really comes from some kind of cesium clock somewhere, and then there is a protocol for distributing and maintaining this clock over the entire network. Frames are sent byte by byte, and ADMs can add drop smaller tributaries into the main SONET SDH stream, and how that is done, that I have explained, that within that frame you can send a lot of bytes. So, you can take out some of the bytes and add in some of the bytes. That is how you take out some of the smaller tributaries and add some of the smaller tributaries. Digital cross connect, which is an optical layer equipment, which is also very important. It cross connects thousands of streams under software control. So, they replace patch panel. So, that is the good thing about the digital cross connect. Under software control, this is coming from, which is the control is coming from the control plane of the switches. You can connect the streams from maybe one fiber to another. So, handles performance monitoring, PDH SONET streams, and also provides ADM functions, that means add drop multiplexing functions. Finally, we have this concept of grooming in SONET. Okay. Grooming means you group the traffic with in some form, okay, so that you want to treat this group in one particular way. Could be that there is a one group of streams for whom you want to give higher priority, or you can want to give higher quality of service. Okay. So, you have to group them together. Similarly, there may be multiple groups. So, grouping traffic with similar destination, QoS, etc., that is a part of grooming. Multiplexing or extracting streams also, so that is also a part of grooming. A narrow, wide or broadband and optical cross connects may be used for grooming. So, if you look at this figure, you have this narrow band, the SONET layer and the optical layer. So, in the narrow band we have this DS0 grooming, and then in the DS1 grooming, so sort of wide band, then in the broadband DS3 grooming. So, the rates are going up, starting from 64 kbps it is going up. Now, when you have gone up to STS-48, that means you are in the optical domain, that means STS-48 is STM16 really. So, that is a high rate, and the point is at that rate most probably you are in the optical, you are well into the optical domain. And then finally, if you can go to the all optical domain, that means wavelength, waveband and fiber grooming. So, there are different levels of grooming depending on what you want to do. Okay. Lastly, we will just talk a little bit about virtual tributaries or containers. We have already talked a little bit about it. This is opposite of STN. So, actually this in some sense that this is called submultiplexing. I mean we were talking about multiplexing, that means different streams coming together to form one very fat or very fast stream. This is the other thing, that how do we sort of differentiate these sub streams within this, which has to do with submultiplexing. Now, STS-1 is divided into 7 virtual tributary groups. By the way, this SDH uses the term virtual containers or VCs. We have talked about VC4 before, we just mentioned it, but they are called VTs in or virtual tributaries in SONET lingo. So, 7 virtual tributary groups, 12 columns each, which can be subdivided further, alright. So, you see that 12 columns each, 7 virtual tributary groups. So, we have got 84 columns. So, this is 84 columns out of the 87 you have in STS-1. VT groups are byte interleaved to create a basic SONET SP. So, if these VT groups are byte interleaved, they may be again extracted from each other. VT 1.5 is the most popular quickly accessed T1 lines within a STS-1 frame. So, the idea is this, that you have a, let us say a T1 line which is approximately 1.5 Mbps line, which is coming out of your, let us say you have a small business and you have a 1.5 Mbps line. So, that is your bandwidth requirement. Now, you want to connect it to a distant location somewhere. Now, so and you do not want your thing to get mixed up with others, alright. So, what you want, but at the same time you cannot, you as a small business, you cannot have an infrastructure of connecting to another location which is wide apart. So, you will go on this public infrastructure or public switched PSTN network, or whoever is maintaining this communication equipment. Usually, I mean the telecom people usually maintain them in most of the places. Anyway, so they have sort of fiber going from one place to another, etc., which contains very high speed links. So, what you want is that your T1 line should join them, sort of get transported over a distance and then go and feed into another T1 line at the destination. That is what you want. So, you want your T1 line sort of should be have a separate sort of existence, and sort of just like in a compartment we have different passengers. Passengers have their own individual entity, but together they are packed into one compartment and then they travel. Similarly, your T1 line is going to ride onto this very fast stream and travel to the destination. So, VT 1.5 gives you a T1 line, alright. So, but how do you sort of find out about the different, I mean how do you separate them in the SP? The point is you require one more level of pointer used to access access it. So, can access a T1 with just 2 pointer operations. So, first from the LOH you remember you go to the SP just as like that. Similarly, you go to the different tributaries or different containers just using one another level of pointer. This is I mean all this flexibility was not there earlier. So, very complex to do the same function in DS3. So, for example, accessing DS0 within DS3 requires full demultiplexing, stack multiplexing, etc. So, it requires a full demultiplexing, that is not required in SONET. The point is that the other streams may go, you know that where in that frame where your bytes really are travelling for the stream or for the container or for the tributary that you are interested in, you just extract it, others keep on travelling as they are. So, you do not demultiplex the whole thing. So, that gives a great advantage of adding and dropping add drop multiplexing. So, this is just a figure showing that you can have various types of lines all feeding into the same infrastructure. You may have, so what we have put over here, DS1 which is 1.544 Mbps, E1 2.048 Mbps, DSIC, DS2, DS3, ATM at 48.384, E4 which is 139.264, ATM is about 150 Mbps, etc. They are sort of travelling, they are getting into different containers. You see from VT 1.5 different tributaries, that is 1.5, 2, 3, 6, etc. It forms a VT group and rides on a higher strength or a higher speed stream. And just as I said that these are sort of identified through a pointer. So, we have this transport overhead. So, we use some bytes for that out of those 87 columns we have. So, we use some columns of that and then we put a pointer which gives to the STS payload pointer. Then there is a VT pointer to the virtual tributary pointer, and this much is the VT SPE within the overall STS-1 SPE which is the payload. Okay. So, this is I mean even now SONET is the most widely used technology in wide area networking that is existing today. Okay. Of course, I mean as you know that as technology grows, maybe we will grow out of SONET. Okay. People are already talking of going out of SONET, because one disadvantage of SONET is that SONET equipment tends to become tends to be expensive. All right. Well, expensive compared to what we think are expensive or cheap today. Okay. And what we think cheap today may sound very expensive tomorrow. That is how the technology grows. So, people are talking about direct transport over the optical layer, etc., etc. So, maybe we will touch those aspects later on, but all that is still in the sort of talking and experimental stage, and on the field actually SDH or SONET equipment is almost everywhere. Okay. All telecom companies are connected through that, and major service providers are use this as a means of transport. Thank you. Good day. So, today we will be speaking about fiber optic components and fiber optic communication. As a matter of fact, this lecture and as well as the next couple of lectures, we will concentrate on fiber optic communication. We have looked at some of the physical layer components of fiber optic systems before. So, we will sort of quickly review that. So, some of the stuff that we will be talking about today is going to be common, and then from that point we will take it up into WDM systems, that means details of how wavelength division multiplexing is done and how systems are handled in the fiber optic domain. This fiber optic domain happens to be very crucial because a lot of traffic in terms of volume, okay, maybe as much as 40 to 50% actually goes through the fiber, and as days are going by and as more and more demand for bandwidth is coming up, fiber optics is becoming more and more important. So, we will be talking about fiber optic components today. So, in fiber optic components, of course, the basic fiber is there, we have already talked about it. So, we will talk a little bit more about this. Then we have light sources and receivers on the two end, because we know in that in fiber optic cables, light is the carrier of information. Then we require these different components like amplifiers, we need couplers, modulators, multiplexers and switches. So, we will look at these components one by one, and then we will start our discussion on wavelength division multiplexing. The next set of components are these multiplexers, filters, gratings. We have talked just a little bit about it. If you look at this wavelength, so these are all wavelength selective devices. Multiplexers, filters, gratings, these are wavelength selective devices. In a wavelength filter, what we want is that suppose a lambda 1, lambda 2, etc., so many are coming, I want only lambda 1 out, okay. Lambda 2, lambda 3, lambda 4, etc., are absorbed or something. Whereas, if you are a multiplexer, I want these different lambdas are coming in different lines, I want them all to be mixed together and use the same line, okay. So, that is a wavelength multiplexer. So, application could be particular wavelength or a particular wave band selection. Wave band is nothing but some contiguous operating wavelengths which are all side by side, okay. If you remember, operating window, whatever be that 1550 or whatever be the window that you are using, there you can have a number of lambdas all side by side. There is a guard band between each of these operating lambdas. So, guard band, and that is given by the ITUT has specified how much guard band, etc., you will have to have. But so, you can have a large number of lambdas all grouped together in that same window. Now, a band out of that, that means a bunch of frequencies out of that you can sort of select instead of just selecting only one frequency. So, that is a wavelength band selection. Static wavelength cross connects or and OADMs. The OADMs is optical add drop multiplexers. We have come across this term of add drop multiplexers in the context of your SONET, but in the optical domain we require optical add drop multiplexers. We will come to that. Equalization of gain, so that is another application. Filtering of noise, ideas used in laser operation and dispersion compensation modules, etc. These are the different applications. One of the standard wavelength selective component is the arrayed waveguide grating. We have seen this before.